Alright, let's look at number 11. In number 11, there's something here that we have to watch out. It's a piecewise function, although these are both differentiable, both continuous. What we need to watch out now is at where they're partitioned, or where they are separated. In other words, f of x is defined as x squared minus x from -2 to -1. And then from -1 to 0, it's defined in this way. So what we will do now is to make sure whether the function is continuous at -1. So what we'll do is look at f of -1. f of -1 is equal to 2. You just plug it in here plug -1 into x squared minus x, because that's where it's defined. They said that x is equal to -1 here. Now the question is, to the right of -1, in other words, as x approaches -1 from the right, we want to make sure that the limit is equal to 2. Well, since the function is defined as 2x squared minus 3x minus 3 from -1 to 0, so that means we will use this function is where we will plug in the value of -1 to find its limit. So the limit of the function as x approaches -1 from the right is equal to 2 times -1 minus 3 times -1 minus 3, and that is equal to 2. So that means that f is continuous on the whole interval, because we've seen that where there might be a break or a discontinuity, we have checked that indeed they are equal to each other, therefore it's continuous at x equal to -1. So f satisfies the continuity condition on the closed interval -2 to 0. Now the next thing we do is take the derivative of f of x in these two, for these two. And the derivative of f prime of x from -2 to -1 is 2x minus 1. And then we substitute the derivative at -1, and we see that it's equal to -3. Now we take the derivative on the other side on the right side of -1, we differentiate this function, and we see that the derivative is equal to 4x minus 3. Now you plug in -1 into this derivative, and we see that f prime of -1 is equal to -7. What does this tell us? This means that their derivatives are not the same. That means on the left side of -1, this is its derivative. On the right side of -1, this is its derivative. So they should have the same derivative on both sides of -1, which tells us that based on these two things, we conclude that f is not differentiable at x equal to -1. So number 11 does not satisfy the hypothesis for the mean value theorem. Alright, what about number 12? Let's look at number 12. Again, these are two continuous functions, but we just want to make sure at where they're separated or where they're different is when x is equal to 2 is when they will differ. So the question is, are they connected at x equal to 2? So what is f of 2? F of 2, we use the top definition of f of x. So we plug 2 into x, and we see that f of 2 is equal to 1. Now we check the limit of the function as x approaches 2 coming from the right. So if it's coming from the right, we have to plug in values, or we have to plug in 2 into the second or the bottom definition of f of x. And that is equal to 6 times 2 minus 2 squared minus 7 is equal to 1. So since the limit is equal to f of 2, then we can conclude that f is continuous on the closed interval from 0 to 3. Now, we've satisfied the continuity condition. Our next question is, well, is it differentiable at x equal to 2? Okay, so for the function on the top, we take the derivative, and that's just equal to 2. And then if we take the this derivative, the derivative of the function at the bottom, that means it's equal to 6 minus 2x. Plug in evaluate f prime at 2. That's just 6 minus 2 times 2, and it's equal to 2. Since the derivative of f of x to the left of 2 and to the right of 2 are equal, we can conclude that f is differentiable at x equal to 2. And so it would mean, therefore, that since that is the only critical part that we have to check out, then we can say that f is differentiable on the interval from 0 to 3. So number 12 satisfies the hypotheses of the mean value theorem on the interval from 0 to 3.